All right, before we get started today, does anybody have any questions regarding any of the web work problems or the ICA problems or anything like that? All right, well, let's jump straight into mesh analysis. Actually, excuse me, nodal analysis. So nodal analysis is a very powerful circuit analysis tool wherein we eventually wind up writing a system of equations using specifically Kirchhoff's current law and Ohm's law, and it allows us to solve directly for all of the unknown voltages in our system, and then we can use our understanding of basic circuit analysis techniques in order to use those voltages to then find any current or any power or anything like that that we are interested in. So I'm going to teach you guys my nodal analysis technique, where I'm going to break it down step by step, and we're going to kind of learn by doing. And what I mean by that specifically is I'm going to give us an example problem to structure things around, and then we'll talk our way through our steps. So the first problem that we're going to work is only going to have current sources in it, so no voltage sources. And voltage sources cause a little bit of a hiccup. So we're going to learn how to address the presence of voltage sources after we get some level of understanding of the basics of nodal analysis. So the circuit that we're interested in is as follows. So I'm going to have over here on the left a 2 ohm resistor. I'm going to have a dependent current source here, direction up, and it's going to have a value of 3 ix. I'm going to have a second dependent current source down here. This guy is going to have a value of 0.8 Vy. Let's put a 10 ohm resistor here. We'll put a 4 ohm resistor here. I'm going to have an independent current source up here. So let's call this guy 2 amps. Let's make this resistor 12 ohms. And lastly, let's put a resistor down here. And let's make this guy 8 ohms, like so. So let's start by saying that this is a pretty darn complicated circuit, okay? We have 1, 2, 3, 4, 5, 6, 7, 8 different circuit elements. None of the resistors that we have can be combined with any of the others. So I guess technically the 12 ohm and the 8 ohm resistor could be thought of as in parallel, or they're in parallel, so we could combine them, but let's just leave it alone for the sake of argument. So there's not really a whole lot of simplification that we could do here. Before I get started, I do need to define what my controlling variables are. So let's say that the current flowing down through this 8 ohm resistor is Ix. So now, since it's controlling that current source, I definitely don't want to combine it with anything else. And I'm going to say that the voltage drop across this 4 ohm resistor is going to be my controlling variable Vy. Okay. So our first step, and I'm going to start out writing the steps over here to the right, is simply going to be to identify all of the nodes in our circuit. So I'm going to identify my nodes, much like I've done with every other thing. I'm going to use different colors. So I'm going to have this red node kind of at the top left of our circuit. Let's do a blue node over here to the right that's going to wind up also wrapping around to the bottom like so. Let's do a green node here to the middle left, and let's do a purple node here to the middle right of the circuit. So ultimately, we only have 4 nodes to deal with here. Okay. Our second step is going to be to assign a reference or ground node for the system. Okay. So we are going to just pick a node, and we are essentially going to assume that the voltage at that node is 0. And that's what we're going to measure all of the other voltages in our system with respect to. Now, we don't have to use 0 as our reference. It just makes the math slightly easier. If you wanted to say that your ground node represented 5 volts, there's nothing remotely wrong with that. Everything else will just get measured with respect to 5 volts. So I learned this using 0 volts as our reference. Again, it's just because it makes the math easier, so I would encourage you guys to do that, but you don't necessarily have to if you don't feel like it. So now let's talk about kind of the ground rules for selecting which node to use as your reference, okay? So in a circuit like this, where there are no voltage sources, generally speaking, I would choose my reference node as the node that is touching the largest number of circuit elements. So our red node is touching 4 circuit elements, our green node is touching 3, our purple node is touching 4, and our blue node is touching, I think, 5. Yeah. So I would tend to choose the blue node as my reference for this particular circuit. That being said, you literally cannot make a wrong decision here, okay? So if you chose the red node as your reference or the green or your purple, you'll wind up getting the same results at the end. So it literally doesn't matter, but from a ease of writing the equations perspective, choosing the node that touches the most circuit elements is the better option. So I'm going to denote that my blue node is my reference node by putting a little symbol down here, and this is the symbol for ground. So now I'm going to treat my blue node as if it were ground or had an electric potential of 0 volts. Okay. Step number 3 is to assign nodal voltages to the remaining non-reference nodes. Okay. So I'm going to go ahead and assign these nodal voltages, and then I'm going to talk with you guys a little bit about what a nodal voltage actually means. Okay. So I'm going to choose to use subscripts that have letters in this case. So like the nodal voltage at the red node, I'm going to call it VA. And the nodal voltage at the green node is going to be VB. And lastly, the nodal voltage at the purple node is going to be VC. Okay, so I've assigned each of those nodes a nodal voltage. Now let me explain what a nodal voltage actually is. Okay, so a nodal voltage is really just a shorthand for a double subscript notation voltage like we talked about on the second day of class. So all of these nodal voltages are measured with respect to ground. So ground is inherently the negative polarity terminal of the voltage, and then whatever node that we've assigned our nodal voltage at is the positive polarity. So this nodal voltage VA is just a shorthand notation for the voltage drop across the 2 ohm resistor. And VB is just a shorthand notation for the voltage drop across that voltage controlled current source. Because again, the positive polarity terminal of the nodal voltage is at the node of interest. The negative polarity terminal is always, always, always at ground. So from this guy, VC could be thought of as the voltage drop across the 8 ohm resistor or the voltage drop across the 12 ohm resistor, and that should make sense because the 8 ohm resistor and the 12 ohm resistor are in parallel, meaning we can easily see that they share the purple node and they share the blue node. Okay, so just to recap, a nodal voltage is literally just a voltage that is defined where the positive polarity terminal is at the node of interest and the negative polarity terminal is always at ground. Okay. So I'm going to go ahead and erase these polarity signs because we don't actually need them. The nodal voltages take care of that. And then before we move on to our next topics or our next steps in nodal analysis, does anybody have any questions, comments, or concerns? Anything not making sense?
Will we do examples where we have voltage sources involved?
Absolutely. So I want us to learn the ground rules first, because voltage sources actually break one of our steps. It seems like it's going to be a bad thing, but it's actually a rather good thing. But I don't want to break one of our steps until we know what those steps are. So after we work an example or two where we only have current sources, then I'll add voltage sources and we'll see how we can adapt this process to accommodate them. Any other questions about what we've done thus far? All right, so now that we're about to start writing equations, I'm going to move my steps over to the left-hand side of the page here. So step number 4 is going to be express the controlling variables for the circuit in terms of the nodal voltages. So just to be really clear here, if our circuit doesn't contain dependent sources, then there are no controlling variables, and we could skip this step, okay? I have intentionally come up with a circuit that has both a voltage as a controlling variable and a current as a controlling variable so that we can see how we can represent both voltages and currents in terms of our nodal voltages, okay? So we're going to start with that current Ix. Okay? So our first equation that we're going to write is going to be for Ix, and we're essentially just going to use Ohm's law, okay? So how I write my equations, particularly for currents, is I do the nodal voltage where the current is starting from. So that would be VC minus the nodal voltage that the current is flowing to, which in this case is just ground, so 0 volts. And then I divide by my resistor value, which in this case is just going to be 8 ohms. So just to recap that, my current starts here and then flows down through the 8 ohm resistor. So it's starting from node C. So that's where this VC came from. It's flowing to ground, which is 0, which is where this guy came from. And since it's flowing through an 8 ohm resistor, I just put 8 ohms on bottom. So that's really nothing more than Ohm's law, just to be clear. That's the voltage drop across the 8 ohm resistor divided by 8 ohms gives us the current flowing through the 8 ohm resistor. Okay. So that's how we're going to express currents. Let me erase these extra lines and things like that. And this is our first equation for this system. Our second equation is going to be for our second controlling variable, which in this case is just going to be the voltage Vy, which is defined as the voltage drop across the 4 ohm resistor. So in this particular case, we are just going to do whatever voltage, nodal voltage is at the positive polarity terminal. So the positive polarity terminal for Vy is at the red node, which has a nodal voltage of Va. So we're going to have Vy is equal to Va, and then we're going to look for whatever nodal voltage is at the negative polarity terminal, which in this case is going to be Vc. So the nodal voltage at the positive polarity terminal gets a plus sign. The nodal voltage at the negative polarity terminal gets the minus sign. So we're going to have Vy is equal to Va minus Vc. Really, that's what we were doing when we were finding the voltage drop across the 8 ohm resistor to define Ix as well. Okay. So one of the most common mistakes that I see students make when they're writing these type of equations is actually usually for the voltage equation. So very, very regularly, I would see a student give me a result that would be Vy is equal to Va minus Vc over 4 ohms. This is incorrect because when we divide voltage by resistance, we wind up getting a current. And we are trying to define a voltage Vy. So just make sure whenever you're defining a voltage that it's literally just going to be one nodal voltage minus another nodal voltage that might happen to be 0. There won't be any resistor value involved. All right, so before we move on from step number 4, are there any questions about how I came up with these two equations? All right. So step number 5 is going to be write a Kirchhoff's current law or KCL equation for each non-reference node. Okay. So for us, that means we're going to write a KCL equation at the red node, a KCL equation or node A, a KCL equation at the green node or node B, and lastly, a KCL equation at the purple node or node C. When we write these KCL equations, we are going to use KCL version 3, where the currents that are exiting the node are considered to be positive, and any currents that are entering the node are going to be negative. Um, Once we write our first equation, I will kind of explain why we're always going to use KCL number 3 when we're applying nodal analysis. Okay. So we're going to start by writing our KCL equation at node A. Okay, so I'm just going to put here KCL at node A. And until you get really familiar with things, I would encourage you guys to actually write on your circuits the currents that you're effectively adding up together. So we're trying to find all of the currents that are leaving node A. So I'm going to identify them in red like this. So the current flowing down through the 2 ohm resistor is leaving node A. The current flowing down through that top dependent current source is leaving node A. The current flowing down through the 4 ohm resistor is leaving node A. And lastly, the current flowing to the right through the independent current source is leaving node A. So I'm going to add all 4 of those currents together, and I'm going to express all of them in terms of my nodal voltages, if at all possible, okay? So at least my resistor currents will be expressed explicitly in terms of nodal voltages. My current sources will behave a little bit differently, and we'll see that when we get to them in a moment, okay? So the current flowing down through the 2 ohm resistor is starting at node A, and it's flowing towards ground. So I'm going to have VA minus 0 over my resistor value of 2 ohms. Okay. Moving on to the current flowing down through my dependent source. So my little red arrow is in the opposite direction of the arrow for the current source. So that means I'm going to need a minus sign. And so I'm going to have minus 3, and I'm just going to put here IX. Now, realistically, I could go ahead and substitute in my relationship for IX here if I were so inclined. I'm going to do that at the end, just so that I don't clutter things up. Okay. The next current that I'm going to write an equation for is the current flowing through the 4 ohm resistor. So it starts at node A and it flows towards node C. So that'll be plus VA minus VC over 4 ohms. And then lastly, I have the current flowing to the right through the independent current source. And since that current source is just pushing 2 amps to the right, I'll just have plus 2 amps is equal to 0. So now let me explain why I'm choosing to use KCL formulation number 3, where the currents that are exiting the node are positive. So when I wrote my KCL equation at node A, notice that all of my VA terms have a positive sign, okay? That's why I prefer to write the currents exiting the node are positive, because I don't get a bunch of extra negative signs strewn about through here. So what you should see is whenever you write your KCL equation at node A, all of your VAs are going to be positive. Whenever we write our KCL equation at node B, all of our VBs are going to be positive. Whenever we write our KCL equation at node C, all of our VCs are going to be positive, and so on and so forth. Okay. So before we move on to our next KCL equation, let me scroll up so we can hopefully see most of the circuit and this equation at the same time. Does anybody have any questions about where any of these terms came from? All right, so now that we're going to write our KCL equation at node B, I would prefer to have some feedback from you guys just so that I can see that you are catching what I'm throwing. Actually, give me just a second. My stylus is acting up, so I need to hook it up to something real quick. All right. So KCL at node B. So I'm going to be adding this current that's flowing up through that dependent source, plus this current flowing to the right through the 10 ohm resistor, plus this current flowing down through the second dependent source together, and setting them equal to 0. So I want to start with the current flowing up. Can anybody tell me how I would represent that current for this KCL equation?
Would it just be 3ix?
Exactly right, Wes. Thank you very much. So I've got 3ix is leaving node B. Now let's do the current flowing to the right through the 10 ohm resistor. Can anybody help me with that one?
VB minus VC over 10 ohms.
Exactly right, Joseph. VB minus VC over 10 ohms. Thank you. And then lastly, I have the current flowing down through that voltage controlled current source. Can anybody help me with that one?
Would it just be 0.8 VY?
Exactly right. So whenever we have a current source, regardless of if it's an independent current source or a dependent current source, it's literally just going to be whatever the current source is supplying. We just need to check the direction of it to make sure that it's pointed the way that we want, right? So in this case, our arrow is down, like the green arrow that I drew is down, and the arrow on the current source is down. So since they're in the same direction, we're going to have a plus sign. So plus 0.8 VY. Thank you again, West. So those are our three currents. We add them together, set it equal to 0, and we're good to move on to our next node, which will be, so actually let me do a thing here. So this is equation 3. Here is equation 4. And lastly here, we're going to have KCL at node C. So I'm going to be adding together these four currents. The current flowing from right to left through the 10 ohm resistor, the current flowing from bottom to top through the 4 ohm resistor, the current flowing from left to right through the 12 ohm resistor, and lastly, the current flowing down through the 8 ohm resistor. Okay. So does anybody want to help me out with the current flowing from right to left through the 10 ohm resistor?
It should be VC minus VB over 10.
Exactly right, Colin, thank you. Now let's do the current flowing up through that 4 ohm resistor. Somebody help me out with that guy.
VC minus VA over 4.
Exactly right, Joseph, thank you. Now let's do the current flowing to the right through the 12 ohm resistor.
VC minus 0 over 12.
Yep, so VC minus 0 over 12. From here on out, anytime that my current is flowing towards ground, I'm just not going to bother writing anything. So I'm just going to call this VC over 12. But VC minus 0 over 12 is absolutely correct. Thank you, West. So VC over 12 ohms. And then the current flowing down through the 8 ohm resistor is just going to be VC over 8 ohms. Set this equal to 0. And this is equation 5. So I have written 5 equations. How many total unknown quantities do I have? So I think I have 5 unknowns. I have my 2 controlling variables and my 3 nodal voltages. So I have a 5 equation, 5 unknown system that I could throw into a computer algebra solver or something like that as is to solve. Or now we're at a place where we can start, making a few substitutions in order to get this down to something that we could solve with our calculator. Okay. So step number 6 is just going to be solve our system of equations. Okay. So here is where I'm going to start doing substitutions. So anytime I see Ix, I'm just going to replace it with my expression for Ix, which is just Vc over 8. And anywhere I see Vy, I'm going to replace it with that equation 2, where Vy is simply equal to Va minus Vc. Okay. So I'm just going to come out here to the right, and I'm going to simplify these guys a little bit. So this guy would look like VA over 2 ohms minus 3 Ix. So that's going to be minus 3 Vc over 8 ohms plus VA minus Vc over 4 ohms plus 2 amps is equal to 0. Let me just double check and make sure I've done my substitutions correctly. So the only thing I had to substitute in was Ix. So I have minus 3 times Vc over 8. So that seems legit. For this guy right here, I've got plus 3 Ix. So that's going to be positive 3 Vc over 8 ohms plus VB minus Vc over 10 ohms plus 0.8 Vy, where Vy is simply Va minus Vc. And I'm going to set this equal to 0. And I believe I have done those substitutions correctly. And then equation 5 doesn't have any Ix's in it, and it doesn't have any Iy's in it. So really, I can just solve this system of 3 equations to be able to get what I'm interested in. So I know that not all of you are super familiar with how to use your calculators to do this. So I updated my license for my virtual TI calculator. And so I'm going to show you guys how to do it with what is effectively a TI 36X, even though it says 30X, this has the layout of a 36. For those of you that have Casio calculators, if you go into the menu, if you hit the menu button, you should be able to find under that menu something that says equation solver. This particular circuit is being solved by a 3x3 system of equations, so that's what you'll be looking for. So for the TI-30X, I'm going to press second and tangent, which brings up my system solver options. And I'm going to choose option 2, which is for a 3x3 system of linear equations, which is exactly what we have. So there are 4 columns on here. The first 3 columns are for the coefficients for our variables. And then the 4th column is going to be our constant terms. So any constants that we have, we're going to wind up moving over to the right-hand side of the equal sign, okay? So let's look at this first equation right here, okay? So my three variables are VA, VB, and VC. So I really just want to figure out whatever the coefficient of VA is. So I have a factor of 1 over 2 from that first term. So I'm literally just going to do 1 over 2 plus I have a coefficient of 1 over 4 from that third term. And then I'm just going to press enter because that's all the VAs that I see. Okay. So I'm going to let my calculator combine all of those fractions and stuff like that for me because I don't want to spend 20 minutes doing basic algebra or whatever, finding, the least common denominators and all that jazz if my calculator can do it for me. So I don't see any VB terms here. So my coefficient for VB is going to be 0. For VC, I have a negative 3/8 from this second term. So negative 3 over 8. And then I also have a minus 1/4 from this third term. So minus 1 over 4. And now I'm at my constant term. So I have 2 amps on the same side of the equal sign as the variable. So when I move that over, it's going to look like -2. So that's how I put that first equation into the calculator. Now I'm going to work on the second equation. So the only thing that I have for VA is this factor of 0.8. So I'm going to have 0.8 for VA. For VB, I have a factor of 1/10. And then for VC, I have a factor of positive 3/8 minus 1/10 minus 0.8. And there are no constant terms, so I'm just going to put 0 there. And now we're down to our KCL at node C equation. My coefficient for VA is negative 1/4. My coefficient for VB is negative 1/10. My coefficient for VC is 1/10 plus 1/4 plus 1/12 plus 1/8. So let me put all that in. And my constant term is 0. And so now, if I press enter again, it should solve this system for me. Let me scroll down here. So the first thing it's telling me is VA. The next thing it's going to tell me is VB. And then the last thing it's going to tell me is the value of VC. So let me pull that calculator back up so we can look at those. Pull it back up. There we go. So for VA, I had negative 32 over 177. For my second variable, which is VB, I have 3028 over 177. And for my third variable, which is VC, I have 176 over 59. So if anybody was following along with their calculators, did you guys get similar results?
Yes, sir.
Good deal. Okay. Anybody with a Casio, were you guys able to follow along? Unfortunately, I don't have a license for the Casio emulator.
Yes, I got the same thing.
Good deal. Thank you, West. Okay, so we've solved this system using nodal analysis. So we know what those three nodal voltages are. So Now let's take this a step further and see what we can do with this information, okay? So I'm going to scroll back up here to the very top, and let's say that I was interested in finding the power supplied by the current controlled current source, okay? So I want to know the power supplied by this guy right here. Anybody have any thoughts on how I might be able to determine that now that I know what my nodal voltages are?
We could find the voltage drop doing VA minus VB, and then the current doing 3 times IX.
Exactly right. So the voltage drop of VA minus VB would be the voltage drop. Let me erase this real quick and write this as maybe CS with positive polarity up here and negative polarity down here. And the reason why I want the voltage with this particular polarity is so that my current is flowing into the negative polarity terminal, and thus I times V is my supplied power, right? So you are 100% correct that that voltage is just going to be VA minus VB, and then we would multiply that by 3IX, where IX is just VC over 8. So just as a kind of a side thing here, the power supplied by my current controlled current source is going to be VA minus VB multiplied by 3/8. So 3 over 8 ohms, I guess, if I want to use units here to do things correctly. And this is going to be VC. Now, for what it's worth, for those of you that have the TI calculators, and this is one of the reasons why I prefer them, is the TI calculators automatically store all of that information. So if I get out of my system solver by pressing clear, and I can only hope that the emulator works the same way that my calculator at home does. Quit. I should be able to just do whatever is stored in my calculator as X minus whatever is stored in my calculator as Y, which is my second variable, times 3 over 8 multiplied by VC was my third variable, so that's Z. And I get my power to be, goodness, negative 19 point something, 339 watts. So this guy was supplying negative 19.339 watts, or it was absorbing positive 19.339 watts. Okay. I could find the power absorbed or supplied by any of the resistors, any of the current sources, anything here with only 1 or 2 more steps, okay? So nodal analysis is very, very powerful because once you know all of the voltages in a circuit, essentially, everything else is pretty straightforward. So before we move on to a second example, how did you guys feel about this process?
It was a little tedious, but it was good.
A little tedious, fair enough. So I'm not going to say that there aren't times where this won't be tedious, because there definitely are. For homework set number 7, I believe problem 7 has you solving an 11 equation, 11 unknown system. I want to be real clear. I did not write that problem. I'm not that much of an asshole, but anyway. So there will be times when it can be very tedious. realistically, if you can't get it down to a 3 equation, 3 unknown system or smaller, you should be using a computer for this stuff. And so with the next problem that I work, I will intentionally give you guys a system where we can't break it down into something that we can solve with our calculators. And I'll show you how to use solve blocks and stuff like that on MathCAD in order to solve these systems using a computer algebra tool. That being said, while this is tedious, I think it's probably less tedious than just throwing everything we know at it and hoping that something sticks, right? So this process, or the step-by-step algorithm that I've shown you guys, lets you do this without really having any guesswork. So there's no, well, what happens if I apply KCL here? What happens if I apply KVL around this loop? There's none of that. It's just, if you do these steps in this order, you will wind up getting the right answer 100% of the time. Okay. Okay, so do you guys want another example with only current sources, or are you ready for me to mess things up and include voltage sources? All right, since nobody's volunteering anything, I'm going to mess things up and include voltage sources. So our process is going to be very similar, but we're just going to have to add a couple of extra steps. Okay. And by a couple, I think it's going to wind up being 3 total. Okay. So I'm going to draw another circuit that we're going to analyze here. So here's another 2 ohm resistor. Let's have a 6-volt voltage source here. A 4-amp current source here. Let's make this guy a 5 ohm resistor. A 1 ohm resistor. Let's make this a 3 ohm resistor. I'm going to put a dependent voltage source here. Let's put positive polarity on the right, negative polarity on the left, and let's make this guy 3Vx. Let's put a dependent current source over here. Let's make this guy 1/4 of Vy. Let's call this guy right here an 8 ohm resistor. This guy right here, a 10 ohm resistor. I'm going to connect everything along the bottom, and then I'm just going to do a rough count to make sure that we can't do it using our calculator. So 1, 2, 3, 4, 5, 6 nodes, 2 controlling variables. So this is going to be like a 7 equation, 7 unknown system. So I don't need to make it more difficult than this. Let's say that the voltage drop across this open circuit here is Vx, and let's say that the voltage drop across this diagonal open circuit here is Vy. Okay. So we have something that's really gross. Okay. All right. So our first 3 steps are going to be the exact same thing as we had before. Okay. So we're going to identify our nodes, assign a reference node, and then assign nodal voltages to all of our non-reference nodes. So let me just write those steps down again. Let's see. Assign nodal voltages to all non-reference nodes. So identifying my nodes, I've got this guy on top, which is going to be in red. I've got this guy on the middle left in green. This guy towards the middle in blue. This guy over here in purple. Let's do this guy over here to the right middle in orange. And let's do this guy on bottom in pink. So 1, 2, 3, 4, 5, 6 total nodes. Okay. Okay. So when we only had current sources and resistors, I said that we would choose our reference node based on whichever node is touching the largest number of circuit elements. Whenever we have voltage sources in our system, I'm going to modify that and I'm going to say that we want to choose our node, or our reference node, to be the node that's touching the largest number of voltage sources. Well, in this particular circuit, our red node is touching 1 voltage source, our blue node is touching 1 voltage source, our purple node is touching 1 voltage source, and our orange node is touching 1 voltage source. So any of those 4 nodes would be a reasonable choice for our reference node. Technically, we could still use the green node or the pink node if we were so inclined. We're just going to wind up having to write slightly more complicated equations if we choose one of those guys, but it's not impossible by any stretch, okay? So I'll let you guys pick which of our nodes is going to be the reference node.
The red one.
The red one. Okay. So, sorry. We're choosing this top node to be the reference. All right, nothing remotely wrong with that. We can work with it, okay? So, sorry, I don't know what happened there. So now I'm going to assign nodal voltages to all of the remaining ones. So let's call this guy on the far left VA, this guy on the middle left VB, middle right VC, far right VD, and then bottom will be VE. Okay. Step number 4 is going to be the same. So we are going to express our controlling variables in terms of our nodal voltages. So we've got two controlling variables, Vx and Vy. So anybody care to venture your opinion on how we would express that voltage Vx in terms of our nodal voltages?
Would it just be VB minus VC?
Exactly right. So it's the nodal voltage at the positive polarity terminal of Vx, which is just Vb, minus the nodal voltage at the negative polarity terminal of Vx, which is just Vc. So 100% right. Vb minus Vc. So there's our first equation. Somebody else tell me what our equation for Vy should be, please.
VE minus VC.
Exactly right. Thank you so much. All right, so there is our second equation. Okay. Now, step number 5 is going to be different. I'm actually going to skip steps 5 and 6 because I want to show you how the voltage sources here wind up breaking things. And then we'll sort out what those other steps need to be here in just a moment. Okay, so I'm going to leave myself some space for step 5. I think that should be fine. Leave myself some space here for step number 6. And then down here, we'll have step number 7, which is going to be to write KCL equations for all remaining non-reference nodes. Okay, so this might seem a little weird, but I'm going to start by writing my equation for node C first, because I want to show you explicitly how voltage sources break things here. Okay, so when we are writing our KCL equation at node C, we're going to wind up adding these three currents together, right? So the current flowing through the 3 ohm resistor is very well behaved. That's just going to be VC over 3 ohms. So let me come down here and write that down. So KCL at node C is going to start with VC over 3 ohms. And the current flowing down through the 8 ohm resistor is also well behaved. That's just going to be VC minus VE over 8 ohms. Now the current flowing to the right through that voltage source is a problem, okay? So it's a problem because there's literally no way to express that current in terms of our nodal voltages. We know that the voltage drop across that voltage source is 3Vx, so the voltage is well behaved and can be expressed in terms of our nodal voltages, but the current can't be. So the best thing that I could do here would be to call this current, I'm going to give it a name here. This is going to be IVCVS from left to right. Okay. So it's the current flowing through our voltage-controlled voltage source from left to right. So I have VC VS, left to right. Set this equal to 0. I've now added another unknown to our system. So that is less than great because this thing started out as a 7-equation, 7 unknown system, and now it turns out that we have an 8th unknown quantity. Okay. So if we kept on trucking and we wrote a KCL equation at node D, we'd run into a very similar problem. Okay. So I have this equation up, which is well defined. I have this equation, this current down, which is well defined. And then once again, I have the current flowing through a voltage source. Okay. And for what it's worth, it really doesn't matter if it is a dependent voltage source or an independent voltage source. Either way, I can't express my current that's flowing through the voltage source in terms of my nodal voltages. So for the current flowing up, that's just going to be 1/4 Vy. The current flowing down is going to be Vd minus Ve over 10. And now I've got to figure out what the hell it is to do with that current. So I'm going to do the same thing that I did a moment ago, and I'm just going to give this current a name, and then we'll move on from there. Okay. So let's call this IVC VS from right to left. So before I move on from here, I want to ask you guys what I hope is a simple question. What's the relationship between the current flowing through our voltage-controlled voltage source from left to right and the current flowing through that same voltage-controlled voltage source from right to left? How are these two terms that I've underlined related to each other?
They're the same, but one's positive and one's negative.
So they are the same thing, but they are in opposite directions. Absolutely right, Wes. Thank you so much. So what I'm going to do in order to eliminate these two extra unknown things is I'm actually going to just add those two KCL equations together, okay? So I know this seems weird, but I'm going to impress you with my logical acumen here. And I'm going to say that it's not going to hurt anything for me to add those two equations together because the equation on the left-hand side is equal to 0, and the equation on the right-hand side is equal to 0. And I firmly believe, and I think the math backs me up here, that 0 plus 0 is still equal to 0. So if I add these two guys together, I wind up getting VC over 3 ohms plus VC minus VE over 8 ohms plus IVC VS from left to right plus 1/4 Vy plus Vd minus Ve over 10 ohms plus IVC VS from right to left is equal to 0. And because these two currents are equal to each other but are in opposite directions, they wind up canceling each other out. So now I've gotten rid of those two extra unknown quantities. So there's nothing wrong with this particular approach, but there's a smarter way to do it, okay? And so now I'm going to introduce you guys to the concept of a supernode, and we're going to go back to some of those skipped steps. Okay? So let me erase this busyness up here. I'll erase these arrows for now too. So whenever I'm performing nodal analysis, anytime I have a voltage source, I will have what's called a supernode, okay? And a supernode is literally just a combination of two or more nodes. So I'm just lumping these nodes, VC or node C and node D together to surround that voltage source, okay? So instead of writing a KCL equation at each node, I'm going to write KCL equations at supernodes. So that's going to be step 6, okay? So step 6 is going to be to write KCL equations for each supernode that does not, I'm going to underline that because it's very important, contain the reference node. So I've drawn this bubble around nodes C and D, surrounding that 3Vx source. And so what I'm going to do now is I'm just going to find the currents that are leaving the supernode, which are those 4 currents that I've indicated. So when I apply KCL at this supernode, so this will be KCL at supernode CD, I believe. Let me double check that. Yep. I'm going to have VC over 3 plus VC minus VE over 8 plus 1/4 VY plus VD minus VE over 10. Is equal to 0. And it's literally the exact same thing I got doing all of this other work. So KCL at node C, then KCL at node D, then adding them together and then canceling out the things that wind up canceling out. So identifying our supernode and then just applying KCL at that supernode changed these 3 equations into a single equation, or a process for getting that single equation that is the result without having to go through all of those subsequent steps, okay? So that's a pretty important concept here in nodal analysis. Anytime we have a supernode that does not contain the reference node, we're just going to find the currents that are leaving that supernode, add them together, and set it equal to 0. So I'm going to erase all of this stuff down here because we no longer need it. All of that information is captured in step 6.
I have a question, Dr. Hartman.
Yes.
So how will that change with the 6-volt one since it's touching the reference node?
Fantastic question. That is literally the next thing I'm going to address, Colin.
My apologies.
No, not at all. I'm glad you are keeping up with stuff. I wish my eraser thing would be faster, or also I wish that I just brought my damn mouse home so I could just select all this and then press delete on my keyboard. Sorry, this is taking so damn long. Okay. So to answer your question, once my computer catches up, there we go. Oh, that went way too far. So let me scroll up here. I'm going to draw a little gray blob around that 6-volt source because it is also a supernode. And as Colin correctly identified, this particular supernode contains ground, and step 6 explicitly says that we only write KCL equations for supernodes that doesn't contain a reference node or ground, okay? So to sort out what we're going to do with that 6-volt source, we actually need to look at that 3VX source again really quickly. Because our supernode contains 2 nodes. So we really need to figure out how we can get 2 equations out of it. And without making you guys guess a whole bunch of times, I'm just going to tell you what's going to happen, okay? So we have our KCL equation for the currents that are leaving the node. We're also going to need to write a voltage relationship equation for that voltage source. And so that's step 5. Okay. So step 5 is write a voltage relationship equation for each. I'm going to put voltage source slash supernode. And this is an attempt to remind you guys that from a nodal analysis perspective, they're the same thing. Every voltage source is a supernode, okay? So that 3Vx voltage source is supplying, obviously, 3Vx voltage. What's the nodal voltage at the positive polarity terminal of that dependent source?
Repeat the question.
What is the nodal voltage at the positive polarity terminal of the voltage-controlled voltage source?
Is it just VD?
It is indeed just VD. What's the nodal voltage at the negative polarity terminal of that voltage-controlled voltage source?
VC.
So we're going to write our voltage relationship equations in the exact same way that we wrote these controlling variable equations for voltages. It's just whatever voltage is at, whatever nodal voltage is at the positive polarity terminal minus whatever nodal voltage is at the negative polarity terminal. So we have 3Vx of voltage is being provided by the source, and that is equal to Vd minus Vc. So for our 6-volt source, Colin, since you asked about it, would you mind telling me what our voltage relationship equation should be?
Shouldn't it just be VB or 6 volts equals VB?
So,
Oh, I'm sorry, would it be negative 6 volts?
so we could have VB is equal to negative 6 volts. I personally would write it as 6 volts is equal to negative VB, just so that we're following the exact same rules. So the positive polarity terminal of this voltage source is at ground, so we'll have 0 minus the nodal voltage at the negative polarity terminal, which is VB. So 6 volts is equal to 0 minus VB, which we could just write as negative VB if we were so inclined. So that's equation 3. This is equation 4. Our KCL at our supernode that didn't contain the reference is equation 5. So we really just need to come up with 2 other equations. Before we do that, does anybody have any questions about the concept of a supernode or how to write a voltage relationship equation or anything like that? All right. So we are now back down to step 7. We're going to write KCL equations for all of our remaining non-reference nodes. So if I scroll back up to our diagram, what are our remaining non-reference nodes? So what nodes do we not have equations for yet?
VA and VE.
Exactly right. And we're only missing 2 equations because we know that this is a 7 equation, 7 unknown system, right? 2 controlling variables, 5 nodal voltages, so 7 total unknowns. We've already written 5 equations. We're just missing 2, and you have correctly identified it's just going to be KCL at node A and KCL at node E. So here is the currents that we're adding together at node A. I'm just going to go ahead and write these so that we have enough time to talk about how to use MathCAD and all of that kind of stuff. So to me, it looks like we're going to have VA over 2 minus 4 plus VA minus VE over 5. So VA over 2 ohms minus 4 amps plus VA minus VE over 5 ohms is equal to 0. Here's equation 6. By the way, if I make a mistake or you think I've made a mistake on any of these, please let me know. Lastly, we're going to have KCL at node E. So that will be this current plus this current plus this current plus this current. So that's going to be VE minus VA over 5 plus VE minus VB over 1. Since my memory is garbage, I'm going to stop there. So VE minus VA over 5 plus VE minus, I think, VB over 1. Now I'm going to have VE minus VC over 8. And lastly, VE minus VD over, I think it was 10 ohms. Let me just double check that. That is correct. And so there is equation number 7. Okay. So now that we have 7 equations for our 7 unknown system, we're at a point where we can simply solve it. So that brings us to our last step. So for this particular circuit, it is rather complicated, and there's pretty much no way in hell we're going to be able to reduce it down to a 3 equation, 3 unknown system without using an incredible amount of algebra and substitutions and stuff like that. Far more than I am willing to sit through and far more than you guys have the time to figure out. So instead, we are going to use a computer algebra tool in order to do all of this grunt work for us. So hopefully you're aware of this, but if you look on our Canvas page, and actually let me look on our Canvas page to make sure I'm not lying to you guys. I believe I have a link that will allow you to download MathCAD either 8.0 or 9.0 for free using our university license. Okay. Yeah, so right here underneath the introduction section, there's a link to download MathCAD Prime 8.0. If you click on it, it brings you to something else. So if I click on this link right here, it's going to ask me for a username and password. The username and password are given right here. It's just MathCAD and then Bulldogs, where the L's are replaced by the letter 1. If I just type that in, now it brings you to all of the instructions. So a third link, this is where you actually get to download the damn thing. And then it has some instructions on setting stuff up. For what it's worth, you need to use the this IP address for our license server and this port. If you don't use this particular server and that particular port, then you won't have access to the university license, and therefore you won't have access to all of the features of MathCAD Prime. And one of those paid only features is the solve block that we are going to use in this class to solve systems of equations that are too large for us to do with our calculators. Okay, so I've already got MathCAD opened. So this is what it looks like, and I'm going to kind of walk you guys through some of the things here. For what it's worth, at the end, I'm going to save this MathCAD sheet and upload it to Canvas so that you guys will have it as a reference as well. Okay, so the first thing I'm going to do is I'm going to put a solve block onto my page. And because I know for damn sure I'm going to need more room because we're working with a 7 equation, 7 unknown system, I'm just going to make this thing bigger. Okay. So this first part of the solve block is where we put in our guess values. So MathCAD uses what's called an iterative solver, much like the numerical solver on your calculator, where you give it a particular value to start from, and then it's just going to keep on solving it over and over and over again until the results that it gets matches what are called our constraints equations, which is the second thing that we're going to put in. Okay. So in a class like Circuits 1, where we're going to be dealing with, quadratic equations and stuff like that very rarely, the guess values that we choose aren't particularly important. But if you had a system that was dependent on the square of something or something cubed or something like that, your guess values become more and more important because the solve block is only going to return one solution, and it's going to return the solution that is closest to whatever your guess value was. If you wanted to have it spit out all of the solutions for a polynomial, you would need to use a symbolic solve thing, which we don't ever have to do in this particular class. So anyway, so this guess value section is kind of like where we would declare our variables at the beginning of a computer program. So I'm going to have my 5 nodal voltages, VA through VE, as well as my controlling variables, VX and VY here. So I'm just going to type in V, and then because I like my things to look neat, I'm going to do control underscore to give me a subscript, and now A. And then I'm going to press shift and then the colon key. And that brings us to our first of 3 different equal signs that MathCAD uses. So this is effectively just assigning a value to this particular variable. So this is a guess, and because I expect there to only be one exact solution, it doesn't really matter what my guesses are. So I, by default, just use 1 volt, okay? I prefer to use units for everything. I understand that sometimes it can be very tedious, so you guys may not, but I will always use units in my MathCAD sheets. If you either should use units or you should completely avoid units. You can't half-ass it. If you half-ass it, it'll give you lots of errors. So I always use units for everything. Okay. So here's my guess for VA. Now over here, I'm just going to do the same thing for VB, VC, VD, VE, and then down here, I'll do VX and VY. Okay. So those are the 7 different things that I'm going to wind up solving for with this particular solve block. For those of you that are trying to follow along, just let me know when you're caught up or if you have any questions, and then I'll, once you let me know I'm good, I'll move on to the next thing. Thank you, West. So the next thing that we're going to do is we're going to enter in our constraint equations, okay? So those are literally just the equations that we came up with when we analyzed our circuit. So we're going to wind up typing all 7 of them in because my memory is garbage. I'm going to have to go back and forth between, this program where we wrote our equations and then, back and forth to MathCAD. And I'm literally just going to put them in the exact same order that we wrote them. So my first equation is going to be Vx is equal to Vb minus Vc. So here I'm going to do Vx, and now I'm going to press Control equals, and it gives me this boldface equal sign, okay? Now over here I'm going to do Vb minus Vc. So what this bold-faced equal sign essentially means is everything on the left-hand side of the equal sign has to be exactly equal to everything on the right-hand side of the equal sign, okay? When I click out of this little thing, we're going to see that the constraint part jumps up to include this guy, okay? So these sections will automatically expand or make themselves smaller to accommodate where we're putting stuff in. I try to keep everything really organized. Sometimes you guys don't. That's your bag of cats. It really shouldn't matter, but I'll, put all of my guess stuff at the top, then all of my constraint equations in the middle, and then lastly, I'll have it solve at the bottom, which is how it's set up for. So my next constraint equation is going to be Vy is control equal to Ve minus Vc. Then I'm going to get into my voltage relationship equations. So my first voltage relationship equation was 3Vx is equal to Vd minus Vc. So 3 multiplied, by Vx is control equal to Vd minus Vc. For what it's worth, that 3, because it is a voltage-controlled voltage source, has units of volts per volt. So those guys would cancel each other out. If this were a, let's say, current-controlled voltage source, I would very much need to use the units of amps per volt. Otherwise, I'd wind up getting an error here when I tried to solve it. So just to let you know, current controlled voltage sources and voltage controlled current sources, you need to use the units on that scaling coefficient if you choose to use units in MathCAD. Let's see, our next equation is 6 volts is control equal to negative VB. And I believe now we're down to our KCL equation at our supernode. So that's going to look like, let's see, VC over 3 ohms plus VC minus VE over 8 ohms. So VC divided by 3. So there's a couple of different ways that you can get the ohm symbol. The first way, and I hate it, is to go into this units thing right here and then scroll down to resistance. And here we can see that it has kiloohms, mega ohms, and ohms. Okay, so that's one way to do it. I am far too lazy to do that every time I want to put an ohm symbol in. So instead, what I'm going to do is I'm going to do Shift W so that I have uppercase W, and then I'm going to press Control G. So that converts that uppercase W into its Greek equivalent, which is capital Omega. I know that that seems dumb, and I'm not saying it isn't, but the reason why it works that way, for what it's worth, is that lowercase w looks like lowercase Greek omega, so capital W gives you the capital Greek omega. Once you do this enough, it'll start to make sense, or maybe I'm just as insane as the people that program this. But anyway, so to get that omega symbol for ohm, it was Shift W for capital W, and then Control G to convert that into Greek. Then I have VC minus VE over 8 ohms. To have it underline everything, I just press the space bar twice. Let's see, what else do we have here? 1/4 VY. So that is a voltage controlled current source. So I have 1/4, and then my units, because it's a voltage controlled current source, are amps per volt. I'm multiplying that by VY. Now I have VD minus VE over 10 ohms. And this is control equal to 0. So now I believe I just have those two KCL equations, one at node A and one at node E left. So let's scroll to get those. So VA over 2 minus 4 amps. So VA over 2 ohms minus 4 amps plus VA minus something. VE over 5 ohms. Is control equal to 0. And now I have that KCL at node E. So that is VE minus VA over 5 plus VE minus VB over, I think it was 1 ohm, plus VE minus VC over, I think it was 8 ohms. I'll check that in a second. Yep, and now VE minus VD over 10. So I've put in my 1, 2, 3, 4, 5, 6, 7 equations for my 7 unknowns. So the only thing that I have left to do is to solve this guy. Okay. So I'm going to scroll down here. I'm just going to make this thing a little bit bigger. What I'm about to do is technically optional, but it is good practice. So I would encourage you guys to just treat it like you have to do it. I'm going to put in a matrix here, and this is going to be a 7x1 matrix. Okay. So essentially what I'm doing with this matrix is I'm giving the computer somewhere to store all of the information that I'm solving for. Okay. For what it's worth, if I have 7 things declared up here, or 7 variables, I have to solve for all 7 of them at the same time. If I tried to only solve for my nodal voltages VA through VE, it would wind up giving me an error. So if I have 7 things in my guess value section, I have to solve for all 7 in the solver section. So here in this matrix, I'm just going to do VA, VB, VC, VD, VE, VX, VY. The order here doesn't particularly matter. Now I'm going to press Shift colon. So I'm just going to store information in all of those individual variables. And in order for the solve block to solve this thing, I just have to tell it to do that by typing find. And now I'm going to put in all those variables again. So whatever order I put things in this matrix, I need to type them out in the exact same order here. Otherwise, they'll get stored in the wrong place. So VA, B, C, D, excuse me, E, X, and Y. And then finally, over here on the right, I'm just going to press the normal equal sign. And if I did this correctly, and I'm pretty sure I did, it should pop up with 7 numbers. So it found that VA was essentially 0 volts, so 4.525 times 10 to the minus 9. So really it's treating it as if it's a couple of nanovolts, but since everything else is on the order of, volts or hundreds of volts and things like that, I would just call that guy 0. And so we found everything else. Okay. So I'll give you guys a couple of moments to catch up if you're following along. Feel free to ask any questions that you may have, and I will happily explain them. I'm also going to set up Zoom really quickly to be able to allow you guys to share your screens in case you are following along and you're getting an error and you want some help. So I have it set to where you guys can share your screen if you want to, and you can share over me if you need to. While I wait for you guys to catch up or ask questions, I'm going to save this so that I can upload it to Canvas here in a few minutes. If you don't have any questions about anything, there's only 10 minutes left of class, so you could bounce if you wanted to. There's also an ICA that you can be working on, all that kind of good stuff.